I want to take a few minutes to review some wave behaviors with you guys and also to look at what happens when waves hit a boundary. And so the first thing we need to define is really what a boundary is. Okay? And a boundary doesn't necessarily have to be a wall. Okay? This is anywhere the media changes. Okay? So moving from air into water, that's a boundary. Moving from a big rope into a thin string, that's a boundary. So anywhere the media changes, we have a boundary. And things happen at boundaries. Okay? The most obvious one is when it's a solid boundary through which the wave can't travel. So if we take a look at that, okay, here I have a wave on a string, and this has got no boundary. And when I send a pulse, right, we can follow the wave to the end. But if I put a fixed end on that, okay, so now there's this thing clamping it over here, and I send a pulse, oh, bang, wave comes back. Okay, now I want you to watch this wave for a minute. It's got two fixed ends. Look at what happens at each end. Okay, that wave flips over. Okay, so it keeps bouncing from one end to the other, one end to the other, one end to the other, but it flips over at each end. Okay, and that's typical of a transverse wave. So I want to make sure that we get that, and that's not all waves. That's a transverse wave or a wave on a rope. Okay, so what we have is when a transverse wave or a wave on a rope hits a fixed boundary, it reflects back inverted. Okay. Now you can't tell from this picture, but if we go and I'm going to change this simulation up a little bit. I'm going to restart it. Now I'm going to have it oscillate, and this is going to get, well, now let's just send two pulses. Okay. I want you to look at these two pulses. Pay attention to them. Okay, do they change their distance apart? No. Are they getting bigger or smaller? No. They're staying the same frequency. They're staying the same distance apart. Okay, they're moving from one end to the other. That's two pulses. So that's something to keep in mind. Okay, when we have two waves on a rope or a whole wave train, okay, reflection does not change. Reflection does not change frequency. Okay. In fact, the thing that determines the frequency of a wave is what creates it. Okay. Frequency is created or determined by the source. It's not a property of the medium. It's a property of the source. Okay. And so speed is a property of the medium. Right? Different media have different speed, but the frequency depends on what's causing it. So when you create a low note using a subwoofer, okay, it's the vibration that's from the sub that creates that low note. A high note from, say, a flute, it's that higher, faster vibration that creates a higher note. So the source creates the frequency. It's the media that determines the speed. Okay? And one more time I want to go back to that simulation, because if we take a look at it, okay, this is a fixed end, and on both ends we have reflection occurring and inverts. Okay, so the reflection is when it bounces back, the inversion is when it bounces back on the other side. Okay, now I'm going to restart that. Okay, but now I'm going to switch it to a loose end. Okay, and now I'm going to send a pulse. Okay, do you see the difference? Okay. Let's restart that. Pulse that again. It comes back on the same side. Okay. When it gets to this end, it flips over. Flips, inverts. Flips, inverts. Okay. But it only has this inversion on the fixed end. It stays on the same side when it's on the loose end. Okay. So if we take a look at what that means we have slightly different behaviors based on what it's running into. Okay, so frequency is determined by the source. Reflection occurs when it hits a boundary, but a loose boundary, well, that was a weird L. A loose boundary Okay, now I'm embarrassing myself. Loose has got two O's. Okay, the loose boundary means that it does not invert. Okay, loose boundary, no inversion. Okay, so it still reflects, it just comes back on the same side. But again, frequency doesn't change, period doesn't change. Okay, that's for a transverse wave, or a wave on a rope, like a wire wave. Okay, now let's say that it moves through to a boundary from one medium to another. Okay, so say you had like a big heavy rope, and into that you have a nice light string. Okay, if you were to send a wave pulse along this string, it would hit this rope and it would start it vibrating. Okay, it would probably vibrate slower since it's got more mass. Okay, but the frequency would stay the same. And since the frequency stays the same and it's a slower wave, of course the wavelength would have to change as well. Anyways, that's a different discussion. Okay, when this wave hits, some of it's going to get transmitted, but some of it's going to get reflected back. Okay, so you can have this occur at not only a boundary through which the wave can't travel, but it can also occur at the boundary between two media. Okay, and I can't model this one very well, but usually what we say is, and this fits our description, when a wave hits a more dense medium, okay, so more mass per unit volume, a more dense medium, the reflection is inverted. Okay, and this is for a transverse wave, or a wave on a rope, or a wave on a wire. Okay, for a longitudinal wave, we actually get a slightly different kind of thing. And there was a lab that you guys may or may not have done. It depends. I know a lot of you guys are gone. But what we did was we took a tube, big long pipe. Okay, and if you make a noise on one end of this pipe, okay, and we close this end, so it was all shut off, we snapped our fingers, pop, okay, and we had a microphone here that listened to the sound, okay, and we timed how long it took the sound to get there and back, and we can get the speed of sound, but we got a wave function, okay, and when you had this end closed, okay, so this is a pressure wave or a longitudinal wave, because a sound wave is longitudinal, okay, you got back exactly the sound that you started with, no inversion at all. Okay, so closed end, no inversion. Okay. But when you open this end, okay, so this is really crazy because you don't have to have that end closed in order to get a reflection. When you open this end, you get an inversion. It still reflects, but it comes back the other way. Okay? And so that's a little bit weird that it would have a reflection there, but then you think about it, it is actually kind of changing media, because it's moving from this air contained in this tube, right? And so as this wave of pressure moves through it, okay, it's going to have high pressure or low pressure, high pressure, low pressure, high pressure, low pressure, high pressure, low pressure. All of a sudden it's not contained in this tube anymore. It's like, whoa, I can do whatever I want, but that means this is a boundary. Okay, so it does bounce back from there. Okay, but it bounces back inverted. Okay, and musical instruments rely on this. Some musical instruments you blow all the way through. It's an open-ended tube. Some musical instruments are closed on one side, and depending on what you've got, you're going to either have this reflection that's inverted or not. Okay, an open end, there is an inversion. A closed end, there is not. Okay, now what I want to focus on today is actually a wave on a wire, or a wave on a string, so a transverse wave. Okay, and I want you to pay attention to what happens when the two waves collide. Okay, so I'm going to go back to my demonstration, and I'm going to restart this, but I'm going to fix both ends. Okay, and so I'm going to send two pulses, pulse, pulse, pods. Okay, let's play that through, pause. Let's step this through. We've got a wave on the bottom and a wave on the top with equal amplitude. Okay? Step, 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 step. You see that? We have two waves still, but they have now basically canceled each other out. That's destructive interference because they are what's called out of phase with each other. Phase is how closely the vibrations match each other. Okay, if I step this through, these waves are what we call 180 degrees out of phase. Okay, and now they're actually in phase with each other. This point right here, the crest of this wave is in phase with the crest of that wave. And if I step this through, of course, it's going to invert right there. Okay, and now they're 180 degrees out of phase. They're completely out of phase, and as they hit each other, they move into each other, cancel each other out, and then keep going. Okay, so two waves can occupy the same spot at the same time. They move through each other. Their amplitudes, depending on if they're in the same spot or not, are either going to interfere constructively or destructively. Now I'm going to send another pulse. I'm going to try to time this just right. Okay, so that I actually, okay, let's just restart this. Let me send a pulse. Let me go to a loose end, and I'm going to pulse, pulse. Okay, and all right. You can see I've got these two waves coming together. I've got these guys are in phase with each other. The two crests are on the same side. They're both moving in the same direction. They're both moving down. So as I step these waves together, now they interfere, but they get bigger, right? Now my amplitude is way bigger, and then they're going to hit each other. They move through each other, and the two waves are back to where they were with their original amplitudes. So depending on if the waves are in phase or out of phase with each other, they can either get bigger or get smaller. Okay? And that's what we call constructive or destructive interference. Okay? So wave on a string, I'm going to say when waves are in phase, a bigger wave results. When waves are out of phase, a smaller wave results. Okay, and by smaller I'm talking amplitude. Bigger I'm talking amplitude. Okay, and so this is actually called the law of superposition. The law of superposition merely states that the amplitude of the combined wave is equal to the algebraic sum of the amplitude of the two incident waves. Okay, so the amplitude of the resulting wave is the sum of the two incident waves, or three or four if you have lots of them, okay, of the incident waves. Now, that's pretty cool because that means if you have a wave that looks like this, okay, and I put in the equilibrium position, and let's draw another wave right below it that has the same zeros. So I'm going to try to go ahead and make this the same wavelength, but it's completely inverted. Okay. Well, this is trying to vibrate up, this is trying to vibrate down, and so the result is going to be a non-wave. Okay. We're just going to have this dead spot. This is actually what noise-canceling headphones do. They listen for this wave, and they make a wave that's opposite of it. But what if, instead of getting this wave, what if we had one that was way bigger? Okay. Well, then our resulting wave, okay, this is going to try to pull this way, this is going to try to pull this way, this wave's bigger. We're going to end up actually somewhere in between. It doesn't have to be completely destructive. It can be partially destructive. Okay? So you got to pay attention to not only which direction the amplitude's in, but also how big it is. Of course, the last case I want to show you is what if the waves vibrate in the same direction. So now I'm going to jump up, down, up, down, up, down. Okay? The resulting wave, I'm going to draw it over here. I've got a lot of stuff going on. Is going to be bigger. The two add up, add up, add up, add up. Okay, so you can have constructive interference or destructive interference. It's just a matter of if the waves are in phase or out of phase. And we saw beats where they were sometimes in phase and sometimes out of phase, and that happened because we had two different frequency waves. Right? So if these are my two waves, and my equilibrium position is somewhere in here and somewhere in here, okay, then you can see this crest and this crest about line up, so it's going to end up bigger. But this crest and this trough line up, so it's going to end up smaller. So we got this loud, soft, loud, soft, loud, soft, loud, softer pattern from repeating constructive and destructive interference. But now I want to take this one step further, and I want to look at what happens if we have a wave contained on a string, okay, and it just bounces back from one end to the other. Okay, so let me go back to this simulation. Okay, and I'm going to restart this, and I'm going to fix both ends. Okay, so neither end is allowed to move. I'm going to pulse, pulse, pulse. Okay, now this doesn't look like much, okay, because it's not a continuous wave. I'm sending individual pulses, and so you get some weird interference patterns going on, but you don't see a whole lot. What I'm interested in is a continuous wave, and for a continuous wave I need a vibrating source. I need this to oscillate. Okay, so if I restart this and I send it to oscillate, okay, now we're going to see some interesting stuff. Okay, now this is crazy because I actually have damping, which in real life there's damping, which is basically friction. Okay, so I'm going to turn damping on. Okay, now this wave looks a little bit weird. It looks like, well, it doesn't really look exactly like what I want it to be yet. So what I'm going to do is I'm going to pull up a video of a wave on a string in real life instead of a simulation. Alright, so what we have here is a wave on a loop, a wave on a string, or a string that's connected to a speaker. Okay, and he's going to make the speaker vibrate at very specific frequencies. And because of that, we're going to see a wave on a string. But I want you to pay attention to this wave. Okay? So he's going to start it at 10 hertz. Now if you look at this, this string looks to be just vibrating up and down in the middle. What's really happening is a wave is starting from one side, going to the other. He's going to increase the frequency to 20 hertz. Now, look at what happened. Okay? Do you see this? Right here in the middle, there's this little dead spot. That's called a node. These maximum displacement things here and here, these are called antinodes. So this is a node at the end, node in the middle, another node at the other end. Okay? And if you look at this, it looks like this string is just vibrating back and forth, back and forth, back and forth. But in reality, we're getting a wave that starts here, vibrates down, then up, hits this side, reflects back, and comes back this way. And right here, it hits the next wave that's being propagated from here. And they interfere destructively here, constructively here. So a node is a destructive interference. So you actually have two waves going on. A wave coming from the source and a wave being reflected back. Okay? And it gives you this cool, this is called a standing wave, where you have nodes and antinodes. If we play this through, okay, you can see there's a node and antinodes. He's going to increase the frequency again. We're going to go up to 30 hertz. Okay? And we get another node right here, another node right here, and 40 hertz, and we'll see even more nodes, we'll see even more loops, okay? And so this is really two waves, a reflected wave and the propagated wave coming from the source. So one is going this way, one's coming this way, and the media tends to vibrate in place. So that's what's called a standing wave, and a standing wave happens because of interference, okay? Standing waves, these occur because a reflected wave interferes with an incoming wave or an incident wave. Okay? And so what you get, depending on the frequency, the media, the speed, okay, it only happens at certain frequencies, is you get one wave that's moving this way, you get its reflection coming back, and so this wave vibrates sort of like this, and that was a bad job. But these dead spots that never ever move, okay, these are nodes. N-O-D-E-S, node, node, Okay, these spots right here in between where you have maximum displacement, these are antinodes. Okay, and this whole thing together, that's called a loop. Okay, now you'll notice the ends of this string is fixed on both sides, and so you only can have this happen at certain frequencies because only certain wavelengths will fit there. Okay, that wavelength is a half a wavelength. You can also have a full wavelength. You can also have 1.5 wavelengths. Okay, but you can't have like 1 3/4 wavelengths because you have to have a node on both ends in order to get that reflection to happen. Okay, and so there will be a couple problems that we're going to look at dealing with reflected waves, incident waves, and nodes and antinodes. All right, good luck.